So last time we studied the linearization coefficients for Hermite polynomials and Charlier polynomials. And we can do similar things for Chebyshev polynomials. This is also quite interesting, but I will skip this part. If you're interested, you can just read the lecture notes, and this is not that difficult compared to Charlier polynomials or Hermite polynomials, so I'll just skip this part. And I'm going to focus on Laguerre polynomials today because I think this is very interesting, not because we have nice combinatorial models for the linearization coefficients, but also there's nice connection with well-known theorem called McMahon's master theorem. So let's begin this section about Laguerre polynomials. So we already defined Laguerre polynomials satisfying this recurrence with alpha parameter. But as before, just for simplicity, we'll only consider the case alpha equals 1 case. So let's write ln of x to be the Laguerre polynomial with parameter alpha being 1. Then of course we can rewrite the recurrence in this way: x minus 2n minus 1 ln minus n squared, and like this. So it's nicer. And we already know that the moment of the Laguerre polynomial is just n factorial, which is of course the number of permutations on n letters. And to find the combinatorial model for a linearization coefficient, we need some definitions. So we already use this notation. Bracket n means the set of integers 1 up to n, and I'm going to use overlined integers. Overline n, bracket means you have overlined integers. You can just think of this as negative numbers or anything like that. Just I'm writing this to distinguish the regular number, the usual numbers. And k and n is the complete bipartite graph on the disjoint union of these two sets. So we have two n elements, and of course I have to define, maybe I should say, graph G's where the vertex set is this and edge set is, you just connect every I and j bar for ij both 1 up to n. So in other words, example K33, of course we can define Kmn in general, but we only need Knn, so I'm only using this. So we have 1, 2, 3, 1 bar, 2 bar, 3 bar, and then you connect them all in distinct parts, like a bipartite graph like this. Okay? And I'm gonna define m of k and n. So generally it means that when you have a graph, this is a set of all possible matchings on the vertex set where you are only allowed to use edges in this graph. So this is the set of matchings. So matching means a graph with single vertex and edges. Matchings on V. Let me just simply write it. This means, for instance, this could be a matching and singleton, and this could be a matching, etc. Okay, you just take the edges from K and N. In other words, a subset of K and N, except that you cannot have two edges like this. Okay. So first, as before, we need a combinatorial model for this. So we will find a combinatorial model. By the way, this is actually simpler than the Charlier case. The Charlier was, I think, is more difficult. I mean, at least the way I presented it is more complicated there. So Laguerre should be somewhat easier. So ln is generating function for all matchings in K and N, where you add -1 to the number of edges and x, number of fixed points, divided by 2. You see, the number of fixed points is always even, because if you have one edge, it will use two edges, two vertices. So we start with 2n vertices, even number of vertices. So whenever you have like k edges, number of fixed points is 2n minus 2k, so always even. So we divide it by 2 because we want the degree to be n. Oh yeah, that's the claim, and let's prove this. So again, let fn x be the right-hand side, and we will prove this by induction. And we will prove that the left-hand side equals the right-hand side by induction on n. Of course, n equals 0 or 1 is true. You can just substitute the number n equals 0, n equals 1 there. So it's clearly true. So now suppose that it's true for, suppose that the statement is true for all k less than or equal to n. And we're going to consider the case n plus 1. So then enough to show the fn satisfies the same recurrence as L. N squared fn minus 1, because then this is ln, this is ln minus 1. The recurrence gives us this, so that we have the result for our holding for n plus 1 as well. Then, okay, so I'm going to write, just for simplicity, I'm going to write this just as a single letter, W, instead of writing this all the time. And then we're going to express this in a different way. So here, let's say 1, equation 1. The right-hand side of 1 is, I'm going to write xfn minus fn minus nfn. I'm separating the terms in certain way so that we can give some combinatorial meaning. And this is equal to summation tau a1. I'm going to express each term using some generating function for the object like matching. Okay, basically it's up to a5, the same thing. Each a1 will be a generating function for this, a2, a3, a4, a5. Okay, so I need to define what ai's are, all right? Here, where a1 is a set of all matchings in the kn plus 1, n plus 1, where, say, let me write it this way. Tau n plus 1 bar are a fixed point in tau, of course. Okay. So it's like you connect this. Oh, sorry, you don't connect this with anything. Okay, so you just leave it there. So they are fixed points. It will contribute exactly 1x because we divide this by 2, and this will not contribute this. So the remaining part is exactly the one, the same thing with the size, the n decreased by 1. So that's exactly this part. Okay, so that's basically the idea. So A2, you can see just connect them, the two n plus 1, n plus 1 bar. So it's tau, the same part where n plus 1, n plus 1 bar is an edge. Okay. So again, you connect these two by an edge, and this part is exactly the same thing, Fn, but because of this, we have minus sign. So we get this exactly, right? That's simple. And A3, now you can guess what this should be. So basically, we connect the n plus 1 with something that is not n plus 1 bar. So say I n plus 1 is an edge, where, of course, I less than equal to 1 n, like that. So n plus 1 is connected to something that is not, this should be I bar. This is connected to something that's not directly below it. And of course, there are n ways to connect this. That gives us minus n. And then the remaining things are no restrictions with n elements at the top, n elements at the bottom. So exactly the same thing. That gives us this, and the same way we do the opposite, like this. This is an edge for I. This. That means this n plus 1 bar is connected to something I, right? Now we have wondered, there are some overlapping things, right? But that's okay. That's something that we can deal with. Here, because now, and we have both this and this. Of course, about different I bar n plus 1, both, say j n plus 1 bar are edges, where ij 1 up to n. This will correspond to this, because we have two edges, like this, n plus 1, n plus 1 bar. If you consider the remaining things, there are n minus 1 edge and vertices at the top, n minus 1 vertices at the bottom. You just freely connect them. That gives us this. And why is this minus? Oh, yeah, that's right. It's a typo. It's not exactly this. The last part is slightly different. So minus, we need minus here. Because these two edges will contribute minus 1, so plus 1. So we should only have this. Because of this minus, we have to put minus. But this is okay. This is pretty good because we have A3 intersect A4. This is not empty, but this is exactly A5. That means A3, A5, union, and you delete this. So you get just the union of A3, A4, because you subtract the intersection. That means 1 is equal to summation, but any A1, A2 are already disjoint, and they are all disjoint with the other sets. So this is like A1 union, A2 union, A3 union, A4. Weight of tau, like that. Because this will cancel the intersection of A3, A4. The others are all disjoint. So we have this. But if you think about it, their union is exactly the whole set. So this is basically Fn plus 1. That's the proof. So we have some interesting cancellation going on, but if you do the cancellation like this, we have a nice combinatorial model. This is something similar to the Charlier case. We also had some cancellation there. Okay, now we have a nice combinatorial model for the regular polynomials. We have, but we need one more definition. But just before that, let me recall you that a derangement is a permutation pi such that pi I is not equal to I for all I, right? It doesn't have any fixed point. That's what a derangement means. And we need to introduce some kind of generalization of this. And I'm going to use the notation that appeared before, fixed integers. And let's say n equals n1 plus dot 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 nk. And if you remember, we defined the j1 dot 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 js, jk set. So we have 1 up to n. We just collect the first n1 elements and then call it j1 and this part j2, etc. We separated this segment 1 up to n into j segments where the ith segment is ji. Okay, and then now we define n1 dot 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 nk derangement is a permutation pi, again in Sn, so the whole thing, you permute all of these elements such that for all S, if I is in Js, then pi I is not in Js. So, in other words, it's best you can just using a diagram. Let's say we have like a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like this. Then so permutation is basically complete matching actually, complete matching on k and n. But you don't want to connect the things in the same part. So it's like a inhomogeneous stuff that we had seen before. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then if you connect something like this, I'm not sure if I'm able to connect them all, but you see, if it looks like this, there's a derangement. But if you have an edge like this, or even something like this, it's not a derangement. That's what derangement means, the n1 dot 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 nn derangement. So it's a kind of has similarity with inhomogeneous matching. So if you, in other words, a permutation can be understood as a perfect matching, and we can say that a homogeneous edge is an edge that connects I and j bar for the same ij in the same j set. Then derangement is basically inhomogeneous complete matching on k and n. So maybe I can write that down. So in other words, derangement is an inhomogeneous perfect matching on this k and n. Okay, they are really the same thing. All right. Now, by the way, what is the usual derangement? Usual derangement is just a 1 dot 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 1 derangement, because you just separate them all like this. So 1 cannot go to 1, 2 cannot go to 2, etc. So that's exactly the condition for usual derangement. Okay, now we are ready to state the theorem. The linearization coefficient is just the number of derangement. I didn't define this, but okay. dn1 dot 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 dnk is the number of all n1 dot 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 nk derangements. Okay, so it's basically the number of derangements or number of inhomogeneous perfect matchings on this. So okay, so it has similar structures. Okay, so proof is not that difficult. If you have all the machineries here, proof is just like the Hermite case, more or less. So let's do the proof. So again, n is n1 plus dot 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 nk. And L, I'm omitting the x. So we can write this using the combinatorial interpretation for each Linear polynomial. This is generating function for homogeneous matchings, right? So in other words, you find tau 1 matching tau k from the matching of k n 1 dot comma n 1 dot 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 k n k n k. In other words, the matching on this is matching on this, etc. Where we have to have this weight, say minus 1 to edges tau 1 dot 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 tau k, x to the fixed point tau 1 plus dot 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 all divided by 2, like this. I just replace this by the combinatorial interpretation. And then we can move this over there, but then this is just a moment. So this is basically this. This is basically this, where I just need to replace this by factorial, right? This factorial. That's what the moment functional does, right? So now we can give some combinatorial meaning. So what does this mean? So just imagine the graph or diagram. We have a bunch of blocks like this, and then the corresponding overlined blocks like this. So L1, we have L1, N1, size N1, size N2, size Nk. So from this, you connect just freely among them. That gives us tau 1. So you basically connect them like this. And then you also connect them like this. Then there are some missing dots, right? Some fixed points. I don't know, maybe something like this. Something like that, right? And then now we have the same number of red dots, top and bottom. So we connect them in like m factorial ways. So basically you connect them all, like a perfect matching. So in the end, we get a perfect matching with, but they may be homogeneous or non-homogeneous like this. So we have a perfect matching with two color. Every edge is colored twice, but we have to have this condition that blue edge is always homogeneous, right? But red edges, we have two choices. So for red edge, but what is the sign? A blue edge has minus sign, and this has minus 1 sign, and red has a plus 1. So if you can change red to blue or the other way around, you can cancel the sign. So the usual way, if there is a homogeneous edge, we can change the color. So you find a leftmost homogeneous edge, say, then you can just change the color. So whenever there is a homogeneous edge, it will be cancelled. So we are left with inhomogeneous perfect matchings, which are exactly the derangement, right? So that's the proof. So it's just like a Hermite case. So I'm not going to give you the details, but that's basically the idea. So it's quite nice. Just yeah. So fixed points looks like you connect things like outside, something like that. So that was nice. And what's also quite interesting is we can find a generating function for this. We can actually enumerate this. So using McMahon's master theorem. So let me explain what that is. Multi-derangement and McMahon's master theorem. Okay, so our goal here is to prove this theorem. K is a fixed integer. Generating function n1 nk non-negative integers. So d n1. So this is the number of derangements n1 n2 nk derangement, and we consider the generating function, but in an exponential generating function way, like. So it's multivariate as n1 nk factorial. Okay. So this is something that we want to compute. But it has a very nice formula like this. 1 minus 2 E2 2 E3 minus k minus 1 EK, where En is the elementary symmetric function. Elementary symmetric function on the letters x1 variables xk. So in other words, it's like 1, I1, they're all distinct. You select k distinct integers from 1 to n, and then you just add this monomial. So it's elementary symmetric function. No, this is reversed. We cannot have this. So this n is the degree of the monomial. We have n variables multiplied. Okay. So it's a nice theorem, and we will prove. There are several proofs, but we will use this theorem. It's called, maybe I can just write down the name of the theorem. McMahon's master theorem. Statement. So A is a matrix. It's some matrix. And F, the statement is not something that you see quite often. It looks a little, statement looks a little strange, but it's a nice theorem. Yeah, that's what I can say. This means you take the coefficient of this polynomial. So it needs I1, Y1, IK, YK, n to the k. So this means this is a function depending on these numbers. So what it does is you compute this. This is a polynomial, multivariate polynomials. You have a bunch of terms there. And then you only collect those whose coefficient is exactly this. And you take only the coefficient. Okay? So it will be a number, or number in terms of A, I, J. So it doesn't involve any y's here because you just consider the coefficient. Okay? So y could be anything. You could take any variables there. So I just took y because x will be used later. So this is just the setting. Then the theorem is the generating function for this capital F by the regular generating function or ordinary generating function is 1 over determinant I, the identity matrix, T A, where T is the matrix, this Ij, delta Ij, so diagonal matrix with diagonal entry I. This is basically a diagonal matrix. Okay, so this is obviously due to McMahon, and he named it a master theorem because he believed that this is there are so many applications to this, so it's a master theorem. We can do many things. Yeah. The more interesting or more surprising thing is this was like more than 100 years ago. It was proved 100 years ago. So McMahon actually wrote a book about, the title is, I think, Combinatorial Theory. It was published more than 100 years ago. So can you imagine reading a book written more than 100 years ago? But this book is still used. Also, you can still read the book, and then there are interesting stuff in it. So it can be considered as one of the first fundamental books on combinatorics. So, yeah. Anyway, this is something that we're gonna use, and I'm not gonna prove this, but I will just use this to prove the theorem here. All right. But first, we need some setting. I'm gonna define this multi-derangement. It's basically the same, almost the same thing as derangement of here. I'm considering multiset, where multiset means it's a set, but we allow multiplicities. Multi-derangement of this multiset is just an arrangement, just like a permutation is an arrangement of letters. Arrangement, say pi 1, ... Again, n is the sum of the ni's. Arrangement of the elements, like in the multiset, meaning that we have n1, n2. You just rearrange them, or you arrange them in any way. So there are many possibilities. So it's called a multi-permutation. But we have to have condition. such that pi I see. Yeah, I think it's easier if I write. Sorry about that. It's like a two-line. I'm going to use two-line notation. So it's like two-line notation. Yeah, I think that's that should be the two-line notation. I'm using two-line notation. So pi 1, pi n, like this, okay? So again, of course, here n1, n2, nk, such that pi I is not equal to I for all I from 1 to k. So you rearrange them, but you don't see anything that column that has like IR. Okay? So again, if these are all 1, then it's exactly the derangement. Okay? This is not exactly the n1, n2, nk derangement, but there is a quite simple relation. So let's say n1 nk be the number of multi-derangement. Maybe I should write this sign here. Multi-derangement of 1 n1 k and k. Okay? Then you can see that this must be equal to the derangement n1 nk derangement divided by n1 factorial nk factorial. Because if you have a derangement, you just write that over here, and then just replace all the first n1 integers here by 1, and then the next n2 integers by 2, etc. Then you get multi-derangement. But of course, ones here that they are all somewhere here, they can be permitted anyway. So that gives you like this. This is just like the number of this is exactly the idea that you compute the number of permutations with some repeated elements. So what we want is basically this part is basically M. So that should be something this. So we want to change this number into something in this form. Okay, and first lemma, maybe in the next page, lemma. This has a nice generating function formula using the coefficient, taking coefficient operator. Of course, A is that means this is 1 most of the time, except I equals j, in that case is 0. So as a matrix, in other words, as a matrix, it's like all one matrix minus identity. This is all one matrix. Okay? So let's prove this. And to prove this, I'm going to consider multi-derangement. let's just consider a multi-derangement and just imagine how we can construct such a multi-derangement. And first, the subword, let's consider the subword pi 1 up to pi n minus n1. So it's like, maybe I can just give you a diagram, something that looks like a diagram. So pi is, it looks like this: 2 pi n1 plus 1, pi n1 plus n2, etc. Like, it looks like this. And what does this look like? Anything but 1. You can put any number here but 1. You can put 1, 2, 3, etc. But you can never put 1 there. So constructing this, constructing this part, let's say this part is the same thing as, basically the same as expanding A11Y1, A1KYK, and 1, which is actually, this is really, this is nothing. The others are all 1s, right? Like this. So how do you expand a polynomial, a product of polynomials? You select one term in each factor. Then, if you expand this, everything appears. Like y2, you select y2 first, and then y3, and then you select y2, and etc. And at the end, you get, let's say, y3. This will give us the word that you can get over here. Because anything but 1 can appear, and the length is n1. So you do the same thing with this part, the second part. The second part, pi n1 plus 1, pi n1 plus n2 can be constructed by expanding the second part, like y1, 0, y2, y3, yk, and 2, and etc., and so on. So that means, in this way, in here, if you expand the polynomials, then you get a word, right? But that's always going to be a multi-derangement, but we want exactly n1 ones there, because the number of ones here must be n1, exactly n1, because we just rearrange them, but we don't change the numbers. We only rearrange them. So here, if you expand this, you get all possible words, potentially multi-derangement. But if you select exactly those with n1 y1 and n2 y2, etc., then you get exactly the derangement that we want, that should be counted over here. That's the proof, actually. That is the proof. So if we collect the terms y1, n1, yk, and k, we get all multi-derangement of 1 and 1, k and k. That's the proof. If you're not convinced, just consider the sums, just work out with n equals 2, I don't know, 8, 1 and 3 equals 3, and then if you do the computation, then you will be convinced that it should be something immediate. Yeah. All right, so now we have interpretation for this. So now we know that this part, which is just m without this, we express that something in this form, something like this. So now we need to evaluate this with that a, right? So that's the next step. Then again, let J sub k is the k by k all one matrix. And the one lemma before proving the determinant, I'm gonna prove a simpler determinant. Determinant of this is 1 minus k. Some linear algebra, but the proof is let lambda 1, lambda k be the eigenvalues, all eigenvalues of jk. Then the characteristic polynomial is the product of these vectors, right? So we know this. So if you can compute all the eigenvalues, then we can just substitute x equals 1, then we get this number, we get the determinant, right? That's the idea. But because this matrix J is very simple, all one, we can just find all the eigenvalues immediately with the correct multiplicities. For example, it has a bunch of zeros. So jk has eigenvalue 0 with eigenvectors. We can find k minus 1 eigenvectors, namely ei minus ei plus 1. It's let's use epsilon, yeah, just to avoid the standard basis vector. This is 1. If you multiply 1 minus 1, then everything is 1, so it'll be 0. So 0 and then 0 times this, so it's 0 is an eigenvalue. This is an eigenvector. So we have found everything except 1. Except one eigenvalue. We have already found the k minus 1 eigenvalues, right? And the last one is also easy to find. K is an eigenvalue. What is the eigenvector? All one vector. Because if you multiply 1, everything is 1. Everything is k. So it's k is also an eigenvalue. So we have found everything. So that means lambda 1 dot 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 lambda k is, if we write this largest first, it's like this. That means determinant of x, the characteristic polynomial is you have zeros, k minus 1 zeros, k like that. Now just substitute x equals 1, then you get this one. Quite simple. Finally, we have the one final lemma. Now we need to compute this matrix. Let A be the matrix like this. Then, and T is like basically the diagonal matrix, x1, xk. Then the determinant of I, Ta equals the determinant, the denominator that we saw before. It has nice expansion like this. Okay, let's prove this. first of all, ik minus ta can, if we write this as the ij entry is bij, then bij is what? Is if I is equal to j, this is 1, and oh, I think, okay, let me write it down. Otherwise, oh yeah, that's right. Because this diagonal matrix ta is nothing but the diagonal entries are all 0, and here is like x1 minus x1, etc. So every row has minus xi, except the diagonal entry, which is 1. So if I equals j, we only have 1 from the identity matrix. Okay. So that is the matrix. So we need to evaluate the determinant. But let's just use the formula for the determinant expansion. The sign and pi pi I. This is the determinant expansion. And now because of this, because it depends on the case whether I equals j or otherwise, I equals j means this is a fixed point of the permutation, right? So we will divide this sum into the cases that the fixed point is a certain set. So H is a subset of K. Actually, H is going to be the set of non-fixed points. So permutation fixed point set is K minus H. So it's a non-fixed point. H is the non-fixed point. And we multiply sign. And actually, we only need to look at I in H. Because if I is not in H, it's just BII, which is 1. Okay? So we do this. But so suppose we fix H, then this if you think about this, the integers not in H, they are all 1. They're all fixed. They don't do anything. So you only do permute those outside you only permute those inside K, inside H. So that you can rewrite this as a smaller set of permutation, like of size H. So this is like the H is still here. And if you think about it, this is exactly the determinant I with a size H, J a size H. Oh, sorry, we have to multiply xi. Because now here, let's see. Is this right? Oh, right. This is not a fixed point. So we always have xi multiplied or xi minus multiplied. So if you consider that, you can all pull out all the xi's, and then you are left with I minus j. But wait, maybe there is something missing. Is this? Yeah, there is some more explanation here, but yeah, that's true.
Where is the sign?
Sign just merged into this determinant. Yeah. think, yeah, you have to think about this carefully, but now here, they are all non-fixed points. But now, if you pull out all the x's, you can also include fixed points there because they don't contribute anything here because fixed points, the diagonal entries are now 0. So we can also include fixed points. So instead of considering this, you can consider all permutations on H fixed with no restrictions at all. Here we have restrictions that all the entries in H, they are not fixed points, but they are, the restriction is gone because this is 0 anyway. In the diagonal entries are 0 anyway. So if you think about that, and then you will see that this is the case. Then we are done because this, if you look at this is exactly 1 minus k. So k was not a good choice here, but yeah. Let's say I is from 0 to h, sorry, k. So this part becomes the size of h is I, so this is now 1 minus I, and you consider all possible subsets of k with I size I, and then you multiply this. This is exactly EI, so EI. But that's exactly what we wanted over here. So that's the proof. Okay. I didn't explain the full details here, but there are some steps that I explained briefly. Right? Okay. Okay, now we have all the ingredients to prove the theorem. So we can complete the proof of the theorem. Let A be this set. Then we know that we prove that this is a determinant of I minus TA. Because of this lemma, we can write the generating function for this in this form, exactly in the McMahon's-Mester theorem, the left-hand side. So that is equal to, by the McMahon's-Mester theorem, equal to this. And then, so this is a Mester theorem, McMahon's-Mester theorem, and also with lemma about M. And this is equal to 1 over this is by the last lemma. So that is the end of the proof. Yeah. Okay, so yeah, that's basically all I wanted to say. There are some other topics that you can study on orthogonal polynomials. Like I mentioned at the beginning of the semester, that there are we have seen only a handful of polynomials like Hermite, Chebyshev, Charlier, and Laguerre, but there are more orthogonal polynomials involving some Q analogs, and I told you that there are some schemes that classify classical orthogonal polynomials and Q orthogonal polynomials like that. So the stuff that we did in this class, like the linearization coefficient or the moments and stuff like that, there are many generalizations of this to other polynomials. And there are also studies of orthogonal polynomials using some statistical mechanics model, and also random matrix theory uses orthogonal polynomials quite often. And yeah, so I think orthogonal polynomial, this topic is still very active, and if you study more, then you will find more interesting things there. And we have 2 more weeks in the next 2 weeks, and you will see some of these examples from the student presentation. So the real active research areas. So yeah, that's it. So I finished my lectures here, and we will resume in the next week from the and there will be a student presentation. Okay, thank you.